Somewhere near the edge of the Large Magellanic Cloud, two dead stars are locked in an orbit so tight and so fast that they circle each other completely once every 6 minutes and 14 seconds. And that orbit is shrinking faster than any comparable pair of stars astronomers have ever measured. The system is called eRASSU J060839957041, first flagged in 2024 by the eROSITA X-ray telescope, an instrument built specifically to scan the entire sky for exactly this kind of faint, fast-changing source. eROSITA flies aboard the Spectre RG spacecraft, and between 2019 and 2022, it completed 4 full passes across the entire sky, cataloging hundreds of thousands of X-ray sources along the way, most of them never studied in this kind of detail before. A single blip in that enormous catalog, this particular source, stood out enough to warrant a much closer look. New analysis, combining years of follow-up observations from NICER, XMM Newton, and the Einstein probe satellite, has now pinned down exactly what it's looking at, and exactly how fast it's changing. Pinning down the exact orbital period wasn't as simple as reading a single clean number off the data either, because eROSITA only revisits any given patch of sky periodically rather than watching continuously. The raw timing data was riddled with what astronomers call aliasing, a kind of measurement ambiguity where several different possible periods can all appear to fit the same sparse set of observations equally well. Untangling the real signal from those false candidates required stitching together years of additional observations from other telescopes into one single, continuous, phase-connected timing solution, essentially cross-checking the pattern against enough independent data points that only one possible period could survive the process. That painstaking cross-referencing is what finally locked in the number, 374.15 seconds, precise enough that researchers can now predict, down to a fraction of a second, exactly when the next eclipse in this system should occur years from now. Both objects in this system are white dwarfs, the dense burned-out cores left behind after a star like our Sun runs out of fuel and sheds its outer layers. A white dwarf typically packs roughly the mass of the Sun into a sphere about the size of Earth, dense enough that a single teaspoon of its material would weigh several tons here on the ground. Finding one white dwarf is unremarkable. Finding two of them orbiting each other this closely, completing a full circuit in barely over 6 minutes, is not. For comparison, Mercury, the fastest orbiting planet in our own solar system, takes about 88 days to circle the Sun once. This pair of stellar corpses is doing the equivalent trip in minutes, not months, packed into an orbit smaller than the distance between the Earth and the Moon. Here's the detail that actually makes this system stand out from other known ultracompact binaries, and there aren't many of those to compare it to. By carefully timing the system's X-ray pulses across multiple space telescopes and connecting those measurements into one continuous, unbroken timing solution, researchers measured not just the orbital period itself, but how quickly that period is shrinking. The result: an orbital decay rate that exceeds even H.M. Cancri and V407 Vulpeculi, the two previous record holders for the fastest known orbital decay in a double white dwarf system. This isn't just a fast binary. It's now the fastest shrinking one on record. The reason the orbit is shrinking at all comes down to a phenomenon this channel has covered in detail before: gravitational waves, the ripples in spacetime predicted by Einstein back in 1916. Any two massive objects orbiting each other radiate a small amount of energy away as gravitational waves, and for most systems, including our Sun and its planets, that energy loss is so vanishingly tiny it would take longer than the current age of the universe to matter at all. Systems this compact and this massive are the exception. Losing orbital energy to gravitational radiation isn't a slow, theoretical background process here. It's an active, measurable engine, steadily dragging the two stars closer together, orbit after orbit, tightening the spiral in a way astronomers can track in real time across just a few years of observation. Using that measured decay rate, the research team calculated what's called the system's chirp mass, a specific combination of both stars' individual masses that determines exactly how strongly the pair radiates gravitational waves. The number that came back, roughly 0.43 times the mass of our Sun, places this system among the most massive of its kind ever identified. A heavier chirp mass means a stronger gravitational wave signal, and a stronger signal is part of why the orbital decay shows up so clearly and so quickly in the data. None of this ends quietly. Systems like this one are on a fixed, calculable countdown toward one of two outcomes, and which one depends almost entirely on the exact masses involved. If the combined mass of the two white dwarfs crosses a specific threshold once they finally merge, the result is a Type 1a supernova, one of the most consistently bright and well-understood explosions in the universe, and one astronomers rely on constantly as a cosmic distance marker, a standard candle, used to measure how far away distant galaxies actually are. If the combined mass stays under that threshold instead, the more likely outcome is a different kind of merger entirely, the two white dwarfs combining into one single, more massive white dwarf, left behind spinning unusually fast and carrying an unusually strong magnetic field, generated by the sheer violence of the merger itself. To be clear about the timeline here, none of this is happening on human timescales. Even at this genuinely extreme rate of decay, the actual merger is still expected well in the future, not next year or next decade. But extreme by cosmic standards and extreme by human standards are very different bars, and this system clears the first one by a wide margin, which is exactly why it's worth tracking closely from here. There's also a reason systems exactly like this one matter beyond their own eventual fate. Extremely compact double-white dwarf binaries, ticking away at orbital periods measured in minutes rather than days or years, are expected to be among the strongest and most persistent sources of gravitational waves in the entire galaxy, the kind of steady, predictable signal that future space-based observatories are specifically being designed to detect. The Laser Interferometer Space Antenna, or LISA, planned for launch in the mid-2030s, is expected to be sensitive to exactly this frequency range of gravitational waves, the low, steady hum produced by systems like this one, long before they ever get close enough to merge. Compact binaries like eRASSU J06083957740114 are sometimes called verification binaries for missions like LISA, meaning astronomers already know they're there, already know roughly how strong their gravitational wave signal should be, and can use them as a known calibration source, a way to confirm a future space-based detector is actually working correctly once it launches. So this isn't just a curious, fast-spinning pair of dead stars sitting quietly at the edge of a nearby galaxy. It's a real-time physics demonstration, actively losing energy to gravitational radiation while researchers watch, a future calibration target for a space telescope that hasn't launched yet, and, somewhere down the line, either a supernova bright enough to help measure the scale of the universe, or the violent birth of a single, strange, rapidly spinning magnetic white dwarf unlike almost anything else known to exist. 6 minutes and 14 seconds. That's how long it currently takes these two collapsed stellar cores to complete one full orbit around each other, a figure precise enough now to predict future eclipses years in advance. Every time you finish reading a headline online, somewhere near the Large Magellanic Cloud, this system has already gone around once, and the orbit is just a little bit tighter than it was the last time anyone checked. Beyond what you can see, but never beyond what you can understand. Subscribe, and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.